Welcome to a journey into one of quantum physics' most startling recent discoveries. For nearly a century, physicists believed that when we measure a quantum system, its wave function irreversibly collapses, the particle's multiple simultaneous states vanish, replaced by a single reality. But what if particles retain ghostly memories of their previous identities? Today, we'll explore the groundbreaking quantum shadow effect, discovered by researchers at Vienna Center for Quantum Science and Technology, a finding that challenges our fundamental understanding of reality and could revolutionize everything from quantum computing to our understanding of black holes and even consciousness itself. Since the 1920s, when Niels Bohr and Werner Heisenberg formulated the Copenhagen interpretation of quantum mechanics, physicists have operated under a seemingly unshakable principle: measurement irreversibly destroys quantum superpositions. This creates what appeared to be a clean break between the weird quantum world and our classical reality. When we observe a particle existing in multiple states simultaneously, that superposition supposedly vanishes instantly, leaving only one definite outcome. This process, called wavefunction collapse, has been a cornerstone of quantum theory for generations. But as we're about to discover, this century-old understanding is being challenged in the most unexpected way. The breakthrough came from the Vienna Center for Quantum Science and Technology, where researchers led by quantum physicist Marcus Arndt made a discovery that shook the foundations of quantum theory. Their experiments, published in Nature Physics last year, demonstrated what they call quantum memory persistence, the surprising ability of particles to retain subtle signatures of their pre-measurement states even after conventional measurement appears to have collapsed them. As Arndt explains, it's as if the particle keeps a ghost of its previous identities. The collapse isn't as complete as we once thought. The team prepared photons in specific polarization superpositions, then subjected them to a standard measurement that appeared to collapse their states. What happened next defied conventional understanding. The Vienna team's revelation came through a technique called weak measurement, where researchers interact with quantum systems so delicately that they extract small amounts of information without entirely collapsing the wave function. This technique itself has a fascinating history. Developed theoretically in the 1980s by Yakir Aharonov and colleagues, weak measurement remained largely a mathematical curiosity until experimental advances in the early 2000s made it physically implementable. The approach involves coupling a quantum system to a measurement device so weakly that minimal information is extracted per measurement, necessitating statistical analysis across many identical preparations. What makes the Vienna experiments particularly groundbreaking is their sequential application of both strong and weak measurements. After the photons underwent what should have been complete wave function collapse through standard measurement, subsequent weak measurements revealed something remarkable: statistically significant correlations with the initial states. These correlations should be impossible if quantum collapse were truly complete. The researchers discovered approximately 3% retention signature, small, but unmistakably present across thousands of trials. This phenomenon has been dubbed the quantum shadow effect, because these residual correlations appear like shadows of the original quantum state, persisting beyond their expected lifetime. Traditional quantum theory predicted that after a strong measurement, no trace of the original superposition should remain detectable. The persistent correlations observed defy this expectation, suggesting that quantum collapse may be better understood as a dramatic transformation of information rather than its destruction. This bridges quantum physics with information theory in unexpected ways. If quantum information isn't truly destroyed during measurement but merely transformed into more subtle correlations, it suggests a fundamental conservation principle for quantum information, a finding that challenges nearly a century of quantum mechanical understanding. The quantum shadow effect could resolve one of the most perplexing paradoxes in modern physics: the black hole information paradox. Since the 1970s, physicists have grappled with the apparent contradiction between quantum mechanics and general relativity regarding the conservation of information. Stephen Hawking's work on black hole radiation suggested information might be permanently destroyed when matter falls into black holes, a conclusion that violates quantum principles. As theoretical physicist Renata Kalosh at Stanford University suggests, this could resolve the black hole information paradox. If quantum information can never be fully destroyed but only transformed, then information falling into black holes might not truly be lost. The quantum shadow effect offers a potential resolution by suggesting that information may be encoded in subtle correlations that were previously overlooked, potentially preserving information even as it crosses a black hole's event horizon. The research also connects to neuroscience through the emerging field of quantum biology. Some theorists propose that quantum effects in microtubules within neurons might contribute to consciousness. If quantum states can preserve aspects of their history, this could provide a physical basis for memory formation at the cellular level. The idea that quantum information persists in subtle forms parallels how memories might be encoded and preserved in the brain. While highly speculative, this connection between quantum shadows and consciousness represents one of the most fascinating potential applications of this discovery, potentially bridging the physical world of particles with the subjective experience of consciousness and memory. The discovery has prompted reconsideration of quantum thermodynamics. The second law of thermodynamics dictates an increase in entropy, but quantum shadows suggest a mechanism by which some ordered information persists despite apparent randomization. This has led to the development of new theoretical frameworks for quantum thermodynamics that incorporate information retention across measurement boundaries. If quantum systems retain echoes of their past states, the sharp distinction between past and present becomes blurred at the quantum level. As Arndt reflects, in some sense, quantum particles live partly in their own history. The present state contains echoes of what came before, a kind of quantum memory that defies our classical intuition about time's arrow. This insight challenges our most fundamental understanding of how time and information flow in the physical world. Beyond the philosophical implications, quantum shadows have the potential to revolutionize quantum computing. Current quantum computers struggle with decoherence, the loss of quantum states due to environmental interactions. If residual quantum information persists after apparent collapse, engineers might harness these shadows to create more robust quantum memory systems. Quantum engineer Lydia Del Rio at Zurich explains, "We're already designing quantum error correction codes that leverage these persistent correlations. It's like having a backup copy of quantum information that survives even when the primary state appears destroyed." This could lead to significant advances in quantum computing stability, allowing quantum bits to maintain coherence for longer periods and potentially overcoming one of the field's greatest challenges. Replicating and expanding upon the Vienna experiments presents significant challenges. The effects are subtle, requiring extraordinary precision to distinguish from experimental noise. Several research groups at MIT, Caltech, and the University of Science and Technology of China are currently working to verify the results using different quantum systems, including superconducting qubits and trapped ions. A particularly promising avenue involves entangled quantum systems. Preliminary work suggests that when two particles are entangled and then separated, measurements on one particle leave quantum shadows not only in that particle but also in its distant entangled partner. This non-local shadow effect could provide new insights into the nature of quantum entanglement itself, potentially revealing even deeper connections between quantum information and spacetime. The theoretical framework for understanding quantum shadows remains incomplete. While some physicists interpret the phenomenon within modified versions of standard quantum mechanics, others view it as evidence for more radical alternatives, such as the many-worlds interpretation or objective collapse theories. A unified mathematical model that fully accounts for quantum shadows while remaining consistent with other quantum phenomena remains elusive. This has sparked intense debate within the theoretical physics community, with different camps proposing competing mathematical frameworks to explain the persistence of quantum information after measurement. The quest for this unified theory represents one of the most exciting frontiers in fundamental physics today, potentially requiring a significant revision of quantum mechanics itself. As researchers continue to explore these quantum shadows, we may need to reconsider not just quantum mechanics, but also our fundamental understanding of information, memory, and the nature of time itself. The discovery that particles retain echoes of their past states challenges our conception of reality as a sequence of distinct moments, suggesting instead a more fluid interconnection between past and present. Quantum particles seem to exist partially in their own histories, with present states containing traces of what came before. This blurs the line between past and present at the quantum level, suggesting that time itself may not flow as linearly as our everyday experience suggests. The quantum shadow effect reveals a reality where information flows across time in subtle, previously undetected ways. What began as anomalous experimental results has blossomed into a rich new area of inquiry spanning fundamental physics, cosmology, information theory, and potentially even neuroscience. As experimental techniques improve and theoretical models evolve, quantum shadows may illuminate not only the afterlife of particles but also the very nature of physical reality and information itself. New detection methods with even greater sensitivity are being developed to probe these shadows more deeply. Researchers are designing experiments to test whether quantum shadows might enable communication protocols that leverage these persistent correlations. Others are exploring whether quantum shadows might explain previously mysterious quantum phenomena like the quantum Zeno effect. The field is rapidly expanding, with new research groups joining the investigation each year, drawn by the profound implications of this discovery. The quantum shadow effect fundamentally challenges our understanding of reality at its most basic level. For a century, we believed that quantum measurement created an irreversible break between quantum possibilities and classical certainty. Now, we discover that particles retain ghostly memories of their previous states, suggesting a more nuanced boundary between the quantum and classical worlds. These findings may resolve long-standing paradoxes in physics, from black hole information loss to the foundations of thermodynamics. They offer practical applications in quantum computing and potentially connect to the mysteries of consciousness itself. Most profoundly, quantum shadows suggest that time, memory, and information are more fluid and interconnected than we ever imagined. As we continue to explore these subtle quantum echoes, we may need to radically revise not just quantum mechanics, but our entire conception of how reality unfolds across time. The discovery reminds us that even in well-established fields like quantum physics, nature continues to surprise us with unexpected depths and connections, inviting us to look beyond apparent certainties to find the ghostly traces of quantum memory that may underlie all of physical reality. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.